Now, we're going to get the next talk by Roman on networking Swiss Army for Go. Round of applause for him.
Okay. Hi, my name is Roman Moore. I'm working for Red Hat as a software engineer, and great to see so many people around. As always, the small rooms are pretty full. And I want to tell you today a little bit about Go and how to solve networking problems with it, and also in general why Go is such a nice language to bridge the gap between providing REST services and still having the possibility to work pretty low level on the node at the same time. And basically I want to go with you through three main points in my talk. First, I want to talk a little bit why Go is so nice for infrastructure service writing. Second thing is I want to introduce you a networking example or a task I had to do to solve. And finally, I want to show you how we can solve that purely with Go. First, let's start with why Go is so nice for writing web services. And one thing is pretty obvious. Compared to languages like C, you can just, for instance, annotate your structs and just marshal the data. And if you run it, you're already done with creating a JSON. That's not something which is so trivial with some other low-level languages, like for instance C. Also, providing REST services is pretty simple. Here you see an example where we are creating a REST service with a /user path. It can take XML or JSON, and there's then even a subpath for it where you can specify the user ID to fetch it, and it takes some parameters, and then you just register the find user callback for looking up the user based on the ID. And what you see here is the Go RESTful framework, which is, for instance, used inside Kubernetes. So far so good, but there are, of course, other languages like Java or Python, Ruby. They all have nice web service frameworks, and there's definitely nothing wrong with using them instead of Go. Might even be better because of, especially with Java, because of the library support and so on. But what Go also provides here is working on the low-level details on your nodes. Here, for instance, that's something you would see if you, for instance, try to use pcap extensions for Python. And when you don't have the pcap devel libraries installed, you will get a message like this if you want to pull in your dependencies. GCC will try to compile an extension for Python, and it will just fail because you don't have the devel libraries installed. And how do you solve that normally? You pull in GCC, pcap devel libraries, and then you can finally add your application. That's a heavy process. Normally you then have to kind of package the results to bring it to a node, and that's not really necessary with Go, because there you can extremely easy access all the low-level details of nodes. And to show you how easy it is to work low-level with Go, I came up with a networking example I had to work on some time ago. It's basically based around VM to host networking. So we have wanted to attach virtual machines to host networks which were already existing without the need to modify the host network too much, and integrate the virtual machines in the host network. For instance, you had an external DHCP server, it should get the DHCPs, the IPs from there and so on. We didn't want to make assumptions like that the network already consists of a bridge or an ordinary interface, and make VTAPs would have been nice to use there, since they gives you some nice reduction to the delays of the network traffic compared to bridges. And finally, since I'm working in the Kubernetes area with virtualization add-ons there, we wanted to have the possibility to ship our code as a single binary without dependencies, so that we can use the pretty common pattern of init containers, for instance, in Kubernetes. So you just put your binary in a container, and then you have to place it somewhere on the host so that management application there or a daemon there can find your binary to use the plugin. And therefore, you don't want dynamic dependencies for your code. If we now look a little bit more detail on the task, what you normally see when you do virtual machine management is you have a bridge on the node, you attach you have your interface attached to the bridge, and then you have the virtual machines here in this case two, this VM and this VM. They both have their own tab devices, they're all attached to the bridge. And if now, let's say, the VM on tab 1 wants to ping the VM with the .3 suffix, it can just reach it, and if it wants to ping the node, which has the .2 address and the 2, that's also no problem. Now with Mac VTAPs, it's a little bit different. There are the advantages that you can directly attach Mac VTAPs to the Ethernet bridge, so to the Ethernet device. You don't have to prepare the node in any way for that. And in principle, that works already. It can talk to every other node, but it can't talk to the node it's currently running on. That's a limitation of Mac VTAP. So the virtual machine on Mac VTAP 1 interface can, without any issues, reach the other virtual machine, and it can also reach every other node in the cluster, but it can't reach the node it's currently running on. So this ping would fail with the .2 prefix. One solution for that is adding extra routes. So you can say that traffic coming from that, from the .4 suffix IP, should be routed over a Mac VLAN on the node, which is also part of the same network. And since this is on the node, finally we can ping the node. And that is actually pretty complex to solve if you want to make that generic, because you need a route for every virtual machine you create. And if you don't want to make any assumptions about the host, and if you don't want to make any assumptions about how the virtual machines gets their IP, I mean, except that it's done by DHCP, it's pretty complex to find a solution to get all the pieces together. What you can do is, if the Mac VTAP 1 device sends a DHCP request, you can steal it with traffic control from the Ethernet 0 device, move it to a bridge, where you then can, which is in promiscuous mode, there you can analyze the traffic and see what's going on. And once you're done with analyzing, you have to re-inject via the Mac VLAN 2 the packet so that it finally gets to the cluster, or that the answer gets back to the Mac VTAP 1 VM. And that's what I'm trying to show you now with Go. And we will start with Wish1 Netlink. That's a Netlink implementation for Go. It's based on the Docker networking library originally, but was since then greatly enhanced. And in general, all libraries I'm presenting here, I'm using them every day, but I never contributed there, so all the thanks go to all the cool developers out there which were writing those libraries. And we will start with something pretty simple here. I'm just importing the netlib library, and let's just list all links on the node. And it's pretty simple. And I'm just printing out the dump objects again. And you see here I have a local network, that's my Ethernet, my Wi-Fi, some virtual bridges, and here I have a Sniffer X device, which we'll use later on. So pretty simple to get it already. That's also pretty simple with the core library of Go, but also nice with Netlink. We can also have a look on the addresses attached. In this case, with link by name, I'm just fetching the low interface and fetching the addresses assigned to the interface, and then just let's print the interfaces. In this case, you will see, okay, the low interface has the typical localhost interface, localhost address. Also, creating interfaces is pretty nice. Let's suppose we want to create a Mac VLAN device. You just create a Mac VLAN struct, also with Netlink, give it a name, you tell it to which parent interface you want to connect it. In this case, my Ethernet device has the Netlink 2, and I've just hard-coded it here. And you can even say in which mode the Mac VLAN should run. And then you just call link add with that. And in this case, I'm then finally fetching it and printing out. And here we go. And here we see the Mac VLAN device. It was created and printed out. And it was down at the stage when I fetched it again. Now we already have the first part of our solution, a small part, but now we've already seen how we can create Mac VLAN devices. And so this part is now solved of our puzzle. Next thing is the next topic we want to do is we now want to create a Sniffer bridge, or a bridge where we want to introspect the traffic. And we want to use traffic control filters to move the packets from the Ethernet device to the Sniffer 0 bridge. One could also try to use IP tables, but that would not help much because Mac VLAN and Mac VTAP interfaces or traffic is so slow in the kernel stack, it never reaches IP tables. So you really have to use traffic control. Also, if you do a TC, otherwise it will just not work. It will just ignore any traffic, and you have no influence on it. That's why you need to use traffic control. So the first part is we're just creating a bridge. Again, you just create a bridge struct, give the bridge a name, add the bridge, set the bridge to up, link set up, set it to promiscuous mode, otherwise we won't see much when we're sniffing the traffic there. And then let's just print from IPA the output so that we see the bridge. Yep. And if I'm going down here now, you see the Sniffer 0 bridge was created, and it's in promiscuous mode and up. So we are one step farther. Now we already have the bridge 2 where we want to introspect the traffic. So let's steal the packets as next. First, to steal the packet, we have to create a ingress queue disk. That's something you need in traffic control so that you can then finally attach your filters to. There are different ingress queue disks, but here I'm just using a standard one, adding it to the interface with the link index 2. And then when we've created the queue disk, we create a U32 filter for traffic control. We tell it that we're interested in the Ethernet packet frame in the value at offset 20, and the 0x44 value. 0x44 is just is the port 68, and that's the port that's the answer from the DHCP server we're interested in. And we then create a filter where we tell the filter on which parent interface it should be located. That's again my Ethernet 0 interface, and that we are interested in Ethernet frames. And then where is the selector now? Oh yeah, and that the filter should contain the selector we prepared. And finally, we also want to tell it that the action it should take if the filter matches is mirroring the traffic. So we just create a netlink.nearMirror action and tell it to which device we want to mirror the traffic. In this case, I had a device called foo, and I'm just taking the index from the interface here. And then finally, filter add. The filter is there, and we will output the resulting filter to see if it really was created. And whoop, there we go. We now see on, where is it? On index 2, that's the device index, a redirect to device foo was created, and we're stealing the package. We're even seeing that, and also that it's mirrored action. So we're farther. We got one step farther. We've now stolen the packet. The next part is introspecting it, and there, Go packet from Google helps you a lot. That's a really nice library for introspecting network traffic, and you normally start by opening a PCAP connection to the interface so that you can sniff on the traffic, and then you tell Go packet what kind of traffic you are trying to introspect on by creating a new packet source. So we can try to run it, and then we see exactly what we didn't want to see, an import from C code. So how can we go around that? And the answer is pretty simple. There is, for instance, from ND layer, a raw packet, which implements the packet reader from Go standard library. I think that's not the correct name. I forgot the actual name of how it's called. But this raw packet allows you to listen on packets. You just give it the interface, and you tell it that you're now trying to listen on Ethernet frames. And that's important here. Here you can do something wrong pretty easily. For instance, if you are really listening on a normal Ethernet device, you obviously see Ethernet frames. But if you're using, for instance, VLANs, and you're creating the filters which we had before, then you probably have to recalculate the offset because you're not really on an Ethernet frame, and the offsets for instance, finding out the port would be definitely wrong. And after we've created the raw connection to the interface, we then just have to implement the read packet data method where we are waiting for packets to read. First, we're creating a data buffer which has the size of the maximum transfer unit of the interface. We read the data into that buffer, and then we are filling in some capture info, like when we captured it, how much we captured, how big the packet is at all. In this case, the reader always reads the whole packet, so it's the same value. And we tell the capture info which interface it was, and then we return the data. And actually there you don't see much, except that it's now compiling and no C library was linked in. I didn't really get to the point to creating a more useful example here. And once we have that, we can use this new packet source from before and listen for packets that are like this, and then have a for loop over these packets which are coming in there. And then we can just take the packet and try to convert it to different layers when we're working on it. In this case, if I want to see if it's on the UDP layer, I just try to convert it to the UDP layer via the layer method, and if something comes back, it's a UDP layer, it's a UDP packet, otherwise we can just continue, we're not interested in it. Then we convert it to a UDP packet, do some, check some calculations on it because we want to resend it later on, that's necessary, otherwise we get a malformed package. And we can also go farther and say we're now only interested in packets with port 68 since the DHCP server is listening there. And yeah, so there is a lot more to Go packet, but that's in general on how you can introspect the traffic there. And we can use it in our example to extract the IP address and MAC address of the DHCP ACK, which is very the valuable information we're interested in. And so now the next part is that we also need routes. Now we have the IP, and now we need to create a route. And to create the route, we need to create a destination IP. That's the IP of the VM. We need to create the gateway to get the address for the via part of the route. And in this case, since I wanted to create the demo in this, the route in this code snippet, I'm also adding a device to the interface where I want to, an address to the interface where I want to create the route. Otherwise, I can't create the route. So I am giving the interface where I want to add the route the address of the gateway, and it can simply be assigned to the interface by add address. Then I'm making sure that the MAC VLAN is in upstate, and finally create the route. I give it the index of the MAC VLAN interface. I give it the destination IP, I give it the gateway ID, and I add the route. And if we now run that, we will see that the right route was added. We are now routing from the VM IP over the MAC VLAN with that IP to the host. And if we go back to our example, we're now on Safari again. We have that part also added. Now we're almost done. What we're now missing is we need to write back the packet after we've read it. And therefore we can again use the raw package and just implement the right packet data, and then we can directly write the package we've read from Go packet with that handler to a different interface again. And so we have that part done. And that's pretty much the talk. Here is an overview of useful libraries I've been talking about now, and also about libraries which I didn't have the time to talk about. Mostly the netlink library, the Go packet and draw packet for packet introspection. Then for IP tables you have from CoreOS IP tables. There is an interesting difference to the other packages. This one requires the IP tables tool on the host. So here I didn't completely fulfill the goal of my talk, but it's still a very useful packet. Also, if you want to send and receive DHCP-X or whatever, you can use the DHCP library mentioned here. Yeah, that's pretty much it. So, questions? Well, the testing strategy in that case. So the question was, what would be my testing strategy for such scenarios? I'm basically just creating isolated bridges, attaching MAC VLANs, MAC VTabs, and all that, and just sending the packets and seeing if it comes. I mean, you need privileges, so it's a little bit harder to test than if you're running unprivileged code, but works pretty well. Does that answer the question? Yeah, sure. Just writing test scripts which are creating the interfaces, and yeah. So, and for instance, the netlink library here has some pretty nice example on how you can write the tests, because they have a lot of tests. So it's very nice place to start looking when you want to automate it. And I mean, we're using parts of that, what I've presented here, for instance, in KubeVirt. And in KubeVirt, we have also end-to-end tests from the user. So you provision a full Kubernetes cluster, installing our add-on, and then we're creating all the objects, and then we're checking the host if that really happens. So, I mean, you have to test it on all layers, starting from directly single nodes with unit tests, basically, up to the whole cluster. Yeah. Okay. Looks like that's it. Thank you.